When you ask ChatGPT a question, you're not just talking to an AI model. You're actually tapping into this huge, incredibly complex system running behind the scenes. And today, we're going to pull back the curtain on one of the most critical pieces of that puzzle, the database, to tell a story of just mind-boggling scale.
So let's start with a number. And wow, it's a number that's almost hard to wrap your head around. 800 million.
Yep, that's how many people OpenAI is supporting with ChatGPT. That's bigger than most continents. It's this massive population all hitting the same service, and they're all relying on the exact same core infrastructure.
So that brings us to the big question. How on earth does a single database handle that kind of pressure without just crumbling? Well, the answer is a total masterclass in engineering.
Okay, so the main challenge here is just explosive growth. We're talking almost unprecedented. When your traffic multiplies by 10 times in a single year, you're pushing your entire system to its absolute breaking point.
And what's really fascinating about this whole story is that OpenAI's solution wasn't some fancy brand new exotic technology. Nope, it was Postgres, a super reliable open source database that's been around for decades. They just had to figure out how to make it do things it was really never designed to do.
And this chart, it just shows you what they were up against. Imagine starting the year with a certain amount of load, and by the end of it, boom, you're dealing with 10 times that. Every system has a limit, and they were getting dangerously close to theirs.
So yeah, with that kind of growth, it was only a matter of time before things started to, crack. The engineers started noticing this really dangerous pattern, a vicious cycle of overload that could take the whole service down.
So here's how it would happen. You'd get a sudden traffic spike, and that would cause the database queries to slow way down. As things get slower, requests start timing out. And what do the apps do? They retry, of course, but those retries just pile on, pouring fuel on the fire and sending the database into a death spiral. And for you, the user, that just means the service gets slow, it gets unreliable, and eventually it's just unusable.
Now, a big technical reason for all this fragility comes down to how Postgres handles updates. So picture this. You need to change just one word in a really long document. Instead of just changing that one word, Postgres actually copies the entire document with your change. This is a process that creates what's called write amplification, and under heavy loads, it just bloats the database and grinds everything to a halt.
So the big question is, how'd they fix it? Well, there wasn't one single magic bullet. It was a whole playbook of really clever, targeted solutions, all designed to relieve pressure and build in some resilience. Let's walk through their strategy.
All right, first up, connection storms. Every time a new request came in, it would try to open a brand new connection to the database, and that would quickly overwhelm it. Their solution was something called connection pooling. Think of it like a bouncer at a super popular club. Instead of letting everyone just rush the door at once, the bouncer, in this case, a proxy called PgBouncer, manages the line and reuses existing spots for new people. It's way more efficient, and it means your requests get handled faster.
And the results? They were staggering. The average time it took just to get a connection dropped from 50 milliseconds all the way down to 5. That's a 90% improvement that makes the whole system feel snappier and takes a huge load off the database.
Okay, next challenge, cache miss storms. So to make things fast, right, they cache a ton of data. But what happens if that cache suddenly fails? Well, you get thousands of identical requests that just flood the database all at once. The solution is it's really clever, cache locking.
And this analogy just explains it perfectly. Instead of the entire office getting up and going to the coffee shop at the same time and creating a huge line, one person goes on a coffee run for everybody. With cache locking, only one single request goes to the database to get the data, and all the others just wait for it to come back. It's a simple idea, but it's what keeps ChatGPT feeling responsive for you, even if some of its internal systems are having a bad day. Then you've got the noisy neighbor problem. You roll out a new feature, you're all excited, but whoops, it has an inefficient query that starts hogging all the database resources, and it slows everything else down. The solution? Isolate the workloads. They basically split traffic into high priority and low priority tiers, running on totally separate database instances. This protects the core experience, making sure one little experiment can't slow down your conversations.
And the playbook didn't stop there, not at all. They were hunting down slow code with aggressive query optimization. They were preventing traffic spikes with multi-layer rate limiting, and they started moving the heaviest operations off to other systems entirely. Plus, they added these crucial safeguards, like being super careful with database changes and building a hot standby that could take over in an instant if the main one ever failed.
All right, so after all that hard work, what did they get?
Well, the results of pushing Postgres this far are, honestly, they're nothing short of remarkable.
They hit 5 nines of availability. Now, to put that in perspective for you, that's less than 6 minutes of downtime in an entire year. For a service at the scale of ChatGPT, that is absolutely world-class reliability. And to handle all your requests, they now run nearly 50 what they call read replicas, and they're placed strategically all around the world. This makes sure that no matter where you are, your requests get served with incredibly low latency.
And this might be the most powerful stat of all. Even with that insane 10x growth in traffic, they had only a single major database incident in the last year. That just speaks volumes about the kind of stability they managed to engineer into the system.
So what's the big lesson here? Well, in their own words, the key takeaway is that PostgreSQL can be scaled to support way bigger workloads than a lot of people ever thought was possible. With the right architecture and just relentless optimization, a classic database can power one of the most demanding apps on the planet.
But for a company like OpenAI, the job is never, ever done. Today's massive scale is just tomorrow's baseline. So what's on the horizon?
Well, they're already working on something called cascading replication. It's a technique that'll let them scale to hundreds more read replicas without crushing the primary database. They're also going to keep offloading those heavy write workloads, and they're even exploring more advanced stuff, like fully sharding Postgres, or maybe even moving to different distributed systems down the road.
Which kind of leaves us with this one big question to chew on. OpenAI's engineers, they solve today's scaling problem. But as these AI models get bigger and bigger and their appetite for data becomes even more voracious, what's going to be the next great infrastructure barrier that we have to break?